So, all right, let's take a look at section 7.2, solving recurrence relations. So the idea here is that, here, I'll get the little thing on here. We want to actually solve it. So what does that mean? So to solve a recurrence relation involving the sequence, right, is to find an explicit formula for the general term a sub n. All right, so that's our goal. In this section, we're going to discuss two methods of solving recurrence relations, the iteration method and a special method that applies to what are called linear homogeneous recurrence relations with constant coefficients. Okay, let's take a look at it. So here's our first example. So here's our relation, right? And now what we want to try to do is we want to solve for, say, a sub n, right? And so what do? We're going to use iteration. So we look at this and we realize we just, actually, you just kind of mess around with this, right? And so if I plug in, I can realize that a sub n minus 1 is a sub n minus 2 plus 3. So if you take your formula for a sub n and you insert that, then you realize that a sub n is, a sub 2 minus, n minus 2 plus 2 times 3. If you repeat that again with this a sub n minus 2, then what you start to see a pattern emerging, right? You see that a sub n is actually also equal to a sub n minus 3 times 3 times 3. So in general, we have this. Just look at this. You keep going, you'll notice that the pattern is that a sub n is equal to a sub n minus k plus k times 3. And that's for every k, as long as it's large enough. So if we set, here's a little trick, you set k equal to n minus 1, right? Then in the last expression right here, then you see that a sub n is actually equal to a1, right? Because you get rid of the n, you have n minus 1, right? 1 plus, and then k is n minus 1, so it's n minus 3 times 3. And that's the formula we're looking for, right? And since we're given the initial condition that a1 is 2, we obtain the explicit formula a sub n is 2 plus 3 times n minus 1. Okay? So that's the process of solving the relation. Here's another example. Solve the recurrence relation right here, right? Sn equals 2 times Sn minus 1. I believe I kind of did this, but let's just look at it. So what we realize is we can keep this up, right? You see that you can also, again, iterate, replace, always keeping the 2 in there. 2 times 2 to the n times S0. And you know that S0, that's the number of subsets with 0 elements is 1, so that's how you get the relation. Sn equals 2 to the n. Okay? All right, let me do, these examples are pretty straightforward. Let's take a look at this example. These we've already done. This is essentially, we did this, I mentioned this last time. You realize that you can always rewrite, it looks like. See what's happening is you rewrite the term in terms of earlier terms, and eventually, if you're lucky, and if the sequence is simple enough, easily defined in terms of very elementary operations, you can eventually track it right back to where you can find it, this 1.1 to the n times 1,000, that sort of thing for population growth or investment growth, as we talked about last time. All right, so here's an example. Let's look at this example. Really a kind of very cool example. Okay, here we find an explicit formula for C sub n, the minimum number of moves, right, which the n-disk Tower of Hanoi puzzle can be solved, right? Okay, let's do it. This is kind of actually very interesting, because let's just go through the calculation and then think about it for a while. Okay, so we know from our previous discussions that C sub n is 2 times C sub n minus 1 plus 1. So here again, we're going through that process of continuously plugging in earlier versions. And what we see, if you follow through the reasoning, it's actually just 2 to the n minus 1 times C1 plus 2 to the n minus 2, and so on and so forth. And what you realize is that's exactly the formula that gives you 2 to the n minus 1. And so that's the answer. Now, 2 to the n minus 1, Now let's imagine this. See, this puzzle is famous because it looks as if, it doesn't look that complicated. But let's suppose that you make one move, right? One of these moves every, second, right? Well, let's see. How large can the puzzle be so that you have enough time in your lifetime? Okay, so what's interesting, so here's a number. Let's imagine that you could make one move every second. You knew the algorithm and you can make one move. I was kind of curious, like how many disks, and is it reasonable to think that how large a puzzle could you solve, say, in 50 years or 1 year? So I did these calculations. So in 50 years, it's that many seconds, right? So you want to solve basically this 2 to the n equals this number, I guess -1 or something, right? And then to do that, you can, I guess, take the logarithm of both sides, base 2, use the rules of logarithms, and eventually you come up with 30.5. So in 50 years, you could solve a puzzle that had like 30 disks. But what's odd is that in 1 year, you could solve a puzzle that had approximately 28 pieces. So as these puzzles get larger and larger, the amount of time required to solve them grows exponentially, right? And so that's a problem. So, okay, let's go on to the next example. Okay, so here, let's look at these. They're called linear homogeneous recurrence relations of order k. So they all look like this, a very specific form. Then the next thing, this is called of order k, right? Since there's sort of k constants in there. Okay, so then you have initial conditions, and if you do that, you generate a unique sequence here. So here's some examples of those, this one and this one, right? And what we're going to try to do, here's another one, right? And these aren't because you're multiplying by n or setting it equal to 2n, so it's not changing sort of linearly. Think of it that way, right? Okay, let's look at this example. So I'm gonna give an example of how to solve this type of a relation, and we're going to see a general theorem in a second here. So we're going to illustrate this. So here's our equation. We're going to try to, so we'll illustrate the general method of solving this linear homogeneous recurrence relation with constant coefficients by finding an explicit formula for the sequence defined by the recursive relation this, with these initial conditions. Okay. So the first thing you do is you think of how you solved, other things of that type. So remember, like if you look at this, we know that S of n was like t to the n, where t in that case was 2, like for example, for this one here, right? And so what we do is we basically do the following. We take S of n equal 2 to the n. Thus, our first attempt at finding a solution of this second order recursive relation, right? We're going to just try something else. We will search for a solution of the form v sub n equals t to the n. Okay? So if v sub n equals t to the n is a solution to this equation right here, right? Well, what do? Well, let's just see what that means. That means that v sub n has to be equal to 5 times v sub n minus 1 minus 6 times v sub n minus 2. So let's plug in t. Let's imagine that this is a solution. So we get t to the n equals 5t to the n minus 1 minus 6t to the n minus 2. Or you just rewrite it, set it equal to 0, you get this. Now, then we're going to divide by t to the n minus 2, and we obtain this quadratic equation, okay? And this equation, in this particular example, happens to have roots t equals 2 and t equals 3. So at this point, right, we do have two solutions, right, S and T, of this 7.29 given by S of n is 2 to the n and t sub n is 3 to the n. So that's of this equation right here, right? And so what do we want to do? It turns out that if you look at this theorem very carefully, you can see that if you have two solutions of a linear homogeneous equation, then if you add them together, this is this u sub n, where we have b times u s sub n plus d times t sub n. This is also another solution, okay? to satisfy this. So, all right, now what do? We plug in our initial conditions. We know that we want 7 to be equal to u0. So you plug in 2 to the 0, 3 to the 0, and you get this. So 7 has to be equal to b plus d, and 16 has to be equal to 2b plus 3d. So that gives you a system of equations, and at some point in your career, you've learned how to solve systems of equations. You can do that, and you find that b is 5 and d is 2. So here's u sub n. You get this solution. And you can check to see that's a solution, right? Satisfies the recursive relation. And the general theorem is this. So here's a wonderful theorem that suppose we have this. This is called a second order linear homogeneous recursive relation with constant coefficients, right? And if S and T are solutions of this, then U equals, this is a sort of a summary of what we just studied in the last example. U equal to BS plus DT is also a solution of this relation. And in particular, it says if R is a root of this equation t squared minus c1t minus c2t, then the sequence R to the n equals 0, are also solutions. Right? Isn't that weird? So if A is a sequence defined by A0 equals C0, A1 equals C1, and R1 and R2 are the roots of this equation, with R1 not equal to R2, that's how we get we need two unique roots, right? Then there exist constants B and D such that A sub n is B times R1 to the n plus D times R2 to the n. So this is how these get solved, okay? There's a proof of it right here, and it just basically follows through what we did in the example. It's kind of a miraculous example, right? And here's a really nice example. Let's look at this one. Let's look at the Fibonacci sequence, because this has some really deep and interesting things that pop out of it, okay? So here's an example. So the Fibonacci sequence is defined by this linear second-order recursive relation, right? We've seen it as Fn equals, right, f sub n minus 1 plus f sub n minus 2, but this is how you write it out as a, as a homogeneous second-order recursive relation, right? So with the initial conditions of f1 equals 1 and f sub 2 equals 1, we begin by using the quadratic formula to solve. So you solve this quadratic formula, and you get these two solutions. T is 1 plus or minus the square root of 5 over 2, right? So thus, according to our theorem, the solution is of the form some number b times 1 plus the square root of 5 over 2 to the n plus d times 1 minus the square root of 5 over 2 to the n, okay? And then here they go through, they actually find these b and d, and here they are, right? So, I mean, yeah, there it is. F sub n is 1 over the square root of 5 times 1 plus the square root of 5 over 2 to the n minus, so there it is. It just seems rather strange, right? Because for each one of these integers, it's an integer. It's kind of bizarre, right? Now, I want to just say a little bit about this number here, this 1 plus the square root of 5 over 2, to show you what a strange number that is. Let me show you something here. This is just a little add-on here. Okay, here. Take a look at this. This was actually seriously studied in mathematics, right? And I'll just write it this way. Maybe you've heard this or seen something like this. This is called a continued fraction. You can think of it as an infinite, right? Let's call it alpha. It's an infinite thing. So the idea is that if you look at this equation, I can rewrite this as alpha equals basically 1 plus 1 over alpha as well, right? In other words, you always see, and this could go on forever, and that's the idea, is that you think of this not so much as being alpha there, but you think of it as a continued fraction, right? Well, if you try to solve this, you get this equation: alpha squared equals alpha plus 1, or alpha squared minus alpha minus 1 equals 0. And this is exactly, I think I wrote this down correctly, This is exactly the, let's see here. Yeah, that's exactly what I had written down here. And if you use quadratic formula on that, you get these two solutions. And then that number right there is called the golden ratio, and it pops up everywhere. So anyway, all right, so I hope this helps you out, and this should help you get through section 7.2. So, all right, thank you very much.